All right, so we move on to the next section, or next chapter in the yellow book, the one which is called linear transformations, or linear maps, or linear operators. That's hence the name of the slide. I put this three different names. These are the three different names to the same idea, to the same concept. Linear maps, linear transformations, linear operators. I think yellow book tries to stick more or less with the first term, with the linear maps, given that many people, many academics in this university work with these maps so often in their, not only in their teaching, but in their research as well, including me. And given that for these academics, including me, these three terms mean the same things, sometimes accidentally in my presentations, I may switch from one term to another. You shouldn't be confused with this. So as far as I remember, Yellow Book officially use the term linear maps, but linear transformations and linear operators, that's the equivalent terms, and you should not make any distinction between these three. So what is it? Normally, when you introduce that formula, you need two sets of vector space, two vector spaces, each of them with their own addition and with their own scaling, but each of them sharing the same field of scalars. Any map which takes the elements of V into elements of W and which is subject, so any mapping of V into W, which is subject to two requirements, A and B. Two requirements that the map takes sum of elements into sum of individual images of X and Y, and the map takes the scaled vector into the scaling of the image. Every such map, we're going to call it linear map or linear transformation or linear operator, identical terms. Normally the vector space V, which sits here, we call it domain of T. The W1, the W sub-vector space, which is the one which receives the values of T, we call it the codomain of T. That's right. So these two are linear spaces. And once again, every map which takes elements of V into elements of W and which is subject to these two requirements, we're going to call it linear map or linear transformation or linear operator. Okay. You will see lots of examples of linear maps. The first set of questions you will probably see in your tutorials will be test that something is a linear map, or otherwise show that something is not a linear map. These are relatively easy sets of questions. When you suspect that something is a linear map, and these questions, they rely on your intuition and insight a lot, after a few examples you will gain that, and you will be capable of judging whether the map is linear or not by just looking at it. I'm sure you will develop this skill quite quickly after a few examples. Yet, even if you see and suspect correctly that the map is a linear map, you still need to present formal justification relying on these two requirements. And otherwise, if you suspect that the map in the question is not a linear map, you need to present a counterexample which shows that it is not a linear map. So in the second part, for the letter, when you need to show that something is not a linear map, you either can produce two vectors which fail this identity, two X and Y which fail this identity, or one vector and one scalar which fails this identity. Or sometimes it's even quicker when you show that one of the simple properties of the linear map fails for that example, if you suspect that the example is not a linear map. And those properties, I'm about to list them. So simple properties which are often attached to linear maps, and which you can use to if you suspect that something is not a linear map, you can use them to formally convince everyone that it is true, your suspicion is correct. So the first one we often mention is this: if you apply a linear map to a zero vector, and we know that every vector space possesses a zero vector, you can do the simple argument. You can always replace your zero vector with a combination like this. Zero scalar times a zero vector, then you can use the P requirement of the linear map. You can factor the scale out, and you end up with a zero vector. So it's the first simple observation, which is always true for any linear map. Linear map takes a zero vector into a zero vector. So if you're trying to, if you suspect that something is not a linear map, that will be the first test to try. You try whether your map takes 0 to 0. If it doesn't, your suspicion is confirmed, you're done. If it does not, either your suspicion is wrong or you need to investigate further. Second property, which is often attached to the linear maps and which is useful when you disprove that something is a linear map, is this: if you take a negative of a vector, again, because of the property B, you can always think of a negative of a vector as a scaling of a vector with a negative number, -1. You can factor this -1 through using this B requirement, like this, and you end up with a negative of T of x. It's not a simple observation, which is always true for linear maps, and which is good if you try to confirm your suspicion that that the map is not linear. The third property, which is on this slide, which is it's a separate property. It's not really that much connected to proving that something is a linear map or disproving that something is a linear map. It's a sort of a combination of these two requirements. I'll mention it because in practice, when you deal or manipulate with linear maps, you rarely use these two separately, A or B. Normally, you just combine them in one single property, and that's how it looks. If you apply a linear map to a linear combination of n vectors, it's a consequence of these two. And remember, these expressions of this type, we call them linear combinations. If you apply a linear map to a linear combination, this will be simply the identical linear combination of the individual applications of T. So, and you can see this through this A and B using the method of mathematical induction. So you do like this. You say, I can treat this term as x, I can treat the rest of this linear combination as y, and I can use once requirement A. That's the usage of it. You see, I just split off first term in my linear combination. Now I can use requirement B to take this λ1 factor in front of my t. The second term, I keep it as it is. And now it's time to do the step of induction, isn't it? Because look at this. We're looking now at t applied to a linear combination, but the number of elements in my linear combination is one less. Originally, I had n elements here. Now I have n take 1. So that's exactly the place where we can just say, by the principle of mathematical induction, if I continue the same two steps sufficiently long, the first step, which relies on A alone, and the second step, which relies on B alone, if I continue these steps sufficiently long, I can take each of these terms similarly out, and I will end up with what I announced, linear combination of individual T of x1, T of x2, T of xn. It's the same linear combination. Yeah. So like I said, in practice, when you deal with the linear maps, when you do different arguments or computations or all sorts of manipulations with linear maps, you rarely just use A or B by themselves on their own. You just use this property free, which is, like I showed you just now, is a consequence of A and B, but it's much more practical, yes, free. We're done with this slide. One extra comment which I'd like to make in relation to the slide is this. I made this comment a few times when we just started discussing with you vector spaces. It's probably this slide gives me another opportunity to emphasize this thing. When you have a vector space, we know, I hope we know it now relatively well, we always have two operations attached to this vector space. We use these two symbols, plus and dot, to denote these operations. In this setting, when you define linear map, there is no any requirement for these two plus and dot to be the same as this plus and dot, even though often they will be very similar to each other. So when you write these two identities for the linear map in the general setting, the plus here and the plus here, even though we use the same symbol, these are different pluses. I made these comments a few times when we discussed with the vector spaces. That's the slide which gives me another opportunity to make the same comment. This is a plus on V, this is a plus on W, because the context suggests that. Here we're plussing the x and y vectors, which are elements of V, and here we're plussing t of xy and t of x and t of y vectors, which are elements of W. And the same story here, dot and dot, even though it's the same dot, is the same symbol, they represent different dots, different scalings. Here we're scaling element in V, and here we're scaling element, which is t of x, that's the element in W. Lambda is any scalar here. Yeah. Any questions? So I'll show you a few simple examples of linear maps. Very basic examples. So the first example which I have on my slide is this one. If you take any map between the real line and the real line, real line, we can think of it as a vector space. I'm sorry. Yeah. You can think of a real line as a vector space. It's the R1. It's a special case of Rn vector space. Here's the example, say AX. That's just simple multiplication. A is a real number, X is a real number. This is a linear map, and it's a very simple check. When you suspect something is a linear map, you need to test two requirements, A and B. Here's my testing. If I apply my F to a sum of two vectors, that's the formula for F here. Now, what we're looking at is just the product of two numbers, A and the bracket X plus Y. For product of numbers, we have something which we know under the term distributive law, and I can distribute A, or in like a more simple language, we can expand, but officially it's a distributive law of numerical multiplication. I can expand each of the AX and AY term. I can just use this identity again. It's f of x and f of y. Property A, or requirement A, of a linear map is verified. Similarly, if I do second property, if I verify second requirement for a linear map, I apply my f to a scaled vector, lambda x. This is a formula for my f. You see, I just intentionally put the brackets in a way to emphasize the way we substitute. We substitute my vector lambda x in place of x here. Now I can rearrange the bracket positions. That's something I can do with numerical multiplications. Everything here is just product of numbers. I rearrange, and then I treat this AX as my f of x. So the second property is verified. It's the simplest possible linear map ever. Just a numerical multiplication by a fixed constant A. Strictly speaking, it's not one example of a linear map. It's many examples, isn't it? I mean, every time I fix a number A, I come up with the example. I fix another A, it's another example of a linear map. So in fact, it might be reasonable to reflect this dependence on A. So in fact, my linear map deserves if you would like to reflect this observation that it's not one single map, for every different value of A, it's a different linear map. We can reflect this by introducing a subindex. That might be a good idea. I'm not going to carry these changing notations across all of the lines here. I'm just telling you, sometimes it's a good practice to reflect this dependence in your notations. Second example on this slide, it's a map between number lines. That's the map which I suggest to test. It's not a linear map this time. Oh, my intuition suggests it's not a linear map. It's a big word actually. I made the slide up, right? I know what's there. But you will realize after a while that your intuition will suggest you that very quickly. It's not a linear map. To confirm this suspicion and to convince everyone else that your suspicion is right, you need to fail either one of the requirements, A or B, of a linear map, or one of the properties we just discussed. The easiest property to fail here is just say that if I apply my f to a 0 vector, which in the current context is a 0 number, the result will be 1, which is not a 0 vector, and hence, which is not a 0 vector, and hence this is not a linear map. And that's all you need to say here. As soon as you saw and as soon as you showed everyone that one of the properties of a linear map failed, you can claim safely that this is not a linear map. Third example, again, it's a simple set of examples. This is the one. It's again a map between the real line and the real line, which is just take every number to its square. Okay. Again, I suspect that this is not a linear map, and I start searching for the property which is easiest to fail, and hence convince everyone that this is not a linear map. This time, this 0 test no longer helps, because 0 vector, which is a 0 number, is taken to number 0. That's why this test is no longer helpful. But the second test, which I listed on a slide before, the test which says that the negative of x is taken to the negative of f of x, that's the one which is useful here. If I try my f on -1, 1 is a vector in the current context, because my vectors in the current context are numbers. If I try my function on -1, the result will be 1, because 6 squared of -1 is 1. But a linear map expects to deliver negative of f of 1. And hence, we failed one of the properties, and that's why it's not a linear map. These are a little bit artificial examples, or you may say very simple examples, because every time we see the real line into real line, real line into real line, very simple vector spaces. In yellow book, most of the time you will be looking at into Rn or Cn vector spaces, and I'll show you some examples of that as well. This is just like I said, these are just simple examples of linear map. One quite non-simple example, which is on this slide, but it's an example of a linear map. It's a differentiation map. You can think of it as a linear map. So it's a fourth example on this. On the slide, it's quite a unique map. You can't see many of such maps. So once you see it, you know its property, and it's another little investment into your intuition for other examples of linear maps. That's the map which does this. That's the map which takes a function into its derivative. F dash here represents differentiation of a function. I need to, of course, in order to formally present this linear map, I need to specify what are the domain and codomain of this linear map. I haven't said a word about that. I have to, in order to make an official formal presentation of this map. Normally, when people give this formal presentation for the differentiation map, the one which takes a function into its derivative, they write something like this. It's a map which takes vector space denoted by this symbol into a vector space denoted by this symbol. The symbol on the right-hand side, we know, when we discuss with you fundamental examples of vector spaces, we discussed this example. We didn't touch much this example in your practice in the yellow book because it's not an easy example to study. But a few examples in the yellow book yet ask you to do something about this vector space. If you remember, anyone in this room remembers what this symbol represents? What kind of vector space this symbol represents? Huh? We saw this vector space. Anyone remembers? Well, if you don't remember, here's your reminder. This is a vector space of all continuous functions on the real line. All continuous functions, not every function, but all of which are continuous. Okay, we discussed this vector space. Yellow book had some examples in relation to this vector space. So the codomain of this map in a formal presentation, it's the collection of all continuous functions. We know it is a vector space. We had this discussion. C1, on the other hand, that's a symbol which you see for the first time. The name it's a collection of all functions which are continuously differentiable ones. So it's a functions which not only continuous, but if it's a functions which if you differentiate that, if you take a derivative of that function, it will also be a continuous function. A typical example which distinguishes these two symbols is this one. If you take a function, say mod x, is it a continuous function, mod x? Mod x, is it a continuous function? Can I claim that the mod x is the element of CR? Can I claim this? Can I claim this? Who said yes? Thank you very much. Yes, I can. Thank you very much. That's a correct observation. Mod x is a continuous function. What about, can I claim that the mod x is the element of C1? Oh, too much. C1R. Is it the function which is not only continuous, we know it is now, I confirm that observation, that claim, but can I claim that this function not only is continuous, but its derivative is also continuous? Can I claim that? No, thank you very much. I can't. So it's a very typical example which distinguishes these two classes. CR and C1R. It's a typical example which in that area. Okay, so formally, when you present differentiation map which takes functions to its derivatives, you present it like that. This is we never discuss why this is a vector space. At this stage, you need to believe me. And I think your belief will be enough. You won't see much of the C1 vector space, let alone C. It's hard enough to study. C1 is even harder to study. So if you believe me it is a vector space, please believe me. C1R, it is a vector space. You can add and all of the axioms of that vector space study. In fact, it is a vector subspace of C, isn't it? Because every continuous functions with a continuous derivative, it is also just a continuous function, isn't it? Because it's just part of a definition. So in fact, C1R is a subspace of CR. So in fact, if you're trying to test that C1R is a vector space, you don't need to check all of the 10 axioms. All you need to check those two, you need to follow the subspace lemma. You need to test that it has a zero vector, it's closed under addition, it's closed under C. All you need to do is this. Because C1R is a subspace in CR. So it's an interesting point to think about. But anyway, back to the linear maps. So we don't need this anymore. We don't need this anymore. We don't need this anymore. And we don't need this anymore. So back to the linear maps. Differentiation, it's a very interesting example of a linear map, one of the fundamental examples of the linear map. In fact, probably I don't know, maybe one day you'll learn it. It's one of the inspiring examples for the whole study of the linear maps. That's how you formally present it. It takes the elements of this vector space into elements of this vector space. And it is a linear map. In order to convince everyone it's a linear map, you need to test requirements A and B from my previous slide, and that's the testing. You apply your linear map to sum of two vectors. In the current context, it's sum of two functions, right? This context, it's the sum of two functions context. This is dash applied to sum of two functions. The nature of dash, that's where we employ the nature of the derivative. We know it very well. When you differentiate a sum, this is as good as taking the derivative of f and g individual and then sum the result. And that is T of f plus T of g. That's why the requirement A is satisfied for differentiation. The same story goes about the second requirement, requirement B. When you compute T of lambda f, it is dash applied to the product lambda f, and we know constants can be taken out of the differentiation. That's another property of the differentiation, which we know very well. So I can write it like this, and that is T of lambda. That's why differentiation, it's a very good example of a linear map. Any questions? Again, I made this comment before. This slide gives me another opportunity to make this comment. Every time you prove something, you can't prove things from the scratch. You rely on something in your background. You rely on something in the past you learned. In these examples, when we prove two linear maps here. It's one. First example was a linear map, and this example number 4 was a linear map. Every time we proved that, we relied on something from our background, from something in the past. Here, that's the key identity in the proof, and that's the key identity in the proof. It's reliance on the properties of numbers. Distributive law of multiplication, and that's the associative law of multiplication. Here, again, these are the key things we borrowed from the past. We knew well before we started studying linear maps that differentiation can be applied in individual terms of a sum. And we knew long before we just started discussing linear maps that scalars can be taken out of the differentiation. That's something we borrowed from the past. And when you prove something, you have to make this explicit. This borrowing you're making from the past, it must be clear, otherwise the argument doesn't count. Any questions? All right, so before we see other examples of linear maps, many of these examples will fit into one single scheme, into one single category, like with the linear with the vector subspaces, sorry. We had these two big categories. The same story with the linear maps. Most of the linear maps you're going to study, they will fit into this one big category. But before we do that, I want to just make one immediate linking, and I can show you the context, or the main idea actually, of a linear map within the context of a vector space. I call it uniqueness of, the slide is called uniqueness of a linear map, yeah, or linear maps. And I'll explain what I mean by that. Okay, so here's my general setting again. I have two vector spaces. One is a domain, the other one is a codomain, vector spaces. I have two vector spaces. I will introduce one extra component into the setting right now. This component is basis. Imagine we know, it's not always the case. For instance, this CR, the vector space of continuous functions on the real line. I don't know if you wondered, nobody ever presented you with the basis for that space, right? I mean, if it comes to Rn or Cn, by now you've done sufficient amount of examples, I think, and you more or less confident with the basis in those spaces, how to find those, how to test for those, how to find presentations of vectors with respect to a given basis. All these standard tasks you more or less have mastered or still mastering, but will master soon. But say if you talk about the vector space of functions, continuous function in the real line, the one we just saw when we discussed with differentiation, do you know a basis in that space? Anyone? This space C of R, class of continuous functions on the real line. Does anyone know a basis in that space? You don't. That's one of the signs why that space is that hard to study. There isn't much of the basis in there actually. Oh, what I mean to say actually. From the top of my head, I can't tell you. that space, I don't think it has a basis in the way you expect a basis. That's one of the reasons, my pause and your inability to answer my question. It's the reasons actually that why that space is so hard to study. That's why we don't bother you with that space too much. Anyway, in the current context, we make things simpler. We just make an assumption that my vector space V has a basis. If this is the case, the things becomes a lot easier to study, and that's the case which is often prevails in the yellow book. So my V has a basis of n elements. So the uniqueness of my linear maps thing, it's this. Look at this, what it says. If I have a map, linear map, or in fact, if I have two linear maps, T and S between V and W, such that, yeah, that's right. So if I have two linear maps between V and W, such that these maps, they deliver the same values on elements of my basis, all n elements of my basis B, then my linear maps are identical everywhere. So my linear maps are identical across the whole vector space V. That is, T is identical S. Sometimes to emphasize this identical statement, people use 3 lines for the equal sign rather than 2 lines for the equal sign. This is what I call uniqueness. So if basically it means that the linear map in the context of finite dimensional linear vector space, so the one which has a finite basis, linear map in such context is uniquely defined by the values on the basis. It has significant practical value. Many questions in the yellow book will ask you to predict a linear map given that you know the values of that linear map on some basis. And this uniqueness lemma, and in fact the proof of this uniqueness lemma, gives you exactly the mechanism how to do that. So look at the proof. The proof actually is a simple one, given that you have all of the baggage from our discussions of bases and vector spaces. So look what it says. Just take a vector, any vector, supposed to be vector here. Oh, not this way, of course. You take any vector in a vector space, given that this is a basis. Given that this is a basis, you can expect that there will be scalars, which represent your vector as a linear combination of your basis. You can expect that. That's the nature of a base, as a definition of basis. Any vector representable uniquely as a linear combination of that basis. So now you can say, if I go after T of V, I can use my presentation in terms of my basis. I can use that. Now, property free, remember this property free of a linear maps. If you apply a linear map to a linear combination, you can just basically do the expansion. That's what I mean when I say you never, it's very rare you use A and B alone. You always use A and B requirements of linear map and in combination, like free. So I can expand, I can apply my linear map individually to every vector and put the scalars after that. Now, given that on basis vectors my T delivers the same value as S, I can replace every T of x1, T of x2, T of xn with S of x1, S of x2, S of xn. This is where we use this assumption of my lemma. And now I can do the reverse, the opposite steps, right? I can now say, I can use this property of linear maps that you can expand. I can use it the other way around. Now I can say this whole thing is just S applied to one single linear combination of x1, x2, and xn, which is, through this relation, is just V. And we're done. We chose a random vector from my vector space, and I presented an argument which shows that T of this randomly chosen vector is the same as S of this randomly chosen vector. It's a very simple argument. but it gives you exactly the mechanism for those questions in the yellow book, where you will be given values of your linear map on elements of some basis, and you will need to reconstruct your linear map on the whole space. That's how you're going to do it, through this representation. That's how you're going to do it, through this identity. That's very often happens in mathematics. Not so much statements are valued, but the arguments behind those things, because they deliver the ideas how to do things. And then you can combine those ideas into one single, individually crafted, beautiful, impressive argument. Any questions? Okay. Now, next example of the linear map, it's more in line, more like a streamline example, the one which you see very often in the yellow book. It will cover 95%, maybe 99% of the examples of linear maps in the yellow book. This is the one which I'm going to call the matrix type linear map. So I chose one of the examples from the yellow book to make this, to deliver this idea, what's the matrix type linear map. So look at this, it's the example, it's a question 2, part A. So that's a map of this type, so it's a map which takes this vector space into this vector space, two-dimensional complex valued vectors into four-dimensional complex valued vectors. Yeah, that's right. So the formula which is given in the question is this. That's a map which has the following formula. For every vector in C2 with components x1, x2, you build a vector in C4 through this formulae. We need to see why this is a linear map. There are different minor variations of the argument, and given that you go to different tutorial groups, your tutors will probably do different variations of those proofs. It is a good idea to exchange, actually. But I'll show you, I'm sorry, what I'm about to do, actually, I'll show you the main driving idea behind all of those variations, in fact. The idea just spins about one single observation. And this observation is this. This vector is connected to this vector through the operation. You know, again, it's a borrowing from the past, from the first semester. A connection between the link between this vector and this vector can be expressed like this. Where this A, it's a matrix. It's a matrix with the components like so. This needs verification, of course, and I'll leave it to you to check this, but it's not really that hard to check. Maybe some of you see this already. That if you multiply this 4×2 matrix with complex entries, well, they are just integers, but still complex numbers, by this vector, the result will be this. And that's the one main idea behind this kind of maps all the time. Is something wrong? Excuse me. Gentlemen. No? Are you sure? Good. Because if something wrong, you should let me know. We will all enjoy. Okay. That's right. So that's the main single idea behind all of these type of maps. You can always convert them. You can always see them through matrix multiplication. So if you're facing the task of showing that something like this is a linear map, you can borrow from the past again, something from, look at this. If I start testing my two requirements of a linear map, so I apply my t to x plus y vectors, I can use this observation right here. Then I can, that's the main idea I borrow from the past. I know from the past that matrix multiplication is the one which is subject to the distributive law. I can apply matrix to every term. I can expand brackets when I multiply matrices. Something I know I can do. That's something from the past, something from the first semester. So I can write this like this. and then I can use my identity again, and here's my property A straight away. The same checks works for the requirement B. If I test T on lambda x, I use the formula. I put the brackets here to emphasize the order of operations. And then I can refer back to the knowledge of matrix multiplications from first semester. I know that the scalar here can be taken out like this. And that finishes the second requirement for the linear map. Argument is every argument always relying on something, always relies on something in the past. You can't make an argument from scratch. There must be something you're using, and your job is to make this explicit, what exactly you use. I'm trying to do it right now on this slide. From this observation, we can make a general statement now. We can say that, I'll frame it as a lemma. If I have a matrix of some size, say m times n, with scalars from a vector from field, then any map like this will always be linear. The same argument, the same two lines work for the proof of that lemma. Nothing actually in these two lines uses the specifics of this particular matrix, or specifics of this particular map. Any matrix multiplication map is linear, and that's why I call these maps matrix type linear maps. Like I said, in yellow book, they will be ubiquitous. 95% of the linear, maybe 99% of the maps in the yellow book, they all fit into this one single category. Any questions? All right, if you don't have any questions, yes.
I was just wondering, with that, could you also prove the linear combinations? Like you showed us previously, like using the previous property, like lambda x plus like mu y. Could you also just go in one line instead of slightly on two lines?
What he's saying is that rather than proving these two separately, can you prove something like this, that the t of lambda, say, x plus mu equals something like this? Yes, you can. I mean, sometimes people do that. Sometimes tutors do that. They, rather than proving these two separately, A and B, they can prove one identity like this, and that is an acceptable way of proving it. I'm happy with that too. So yes, you can do that. Any other question? Okay, I'll show you one extra example of a linear map. It's another one of the fundamental examples of linear maps. Another example which actually inspiring the whole study of linear maps, like differentiation example. Unlike differentiation example, which is not in your reach, to be actually honest, it's a difficult map, given that the underlying vector spaces are difficult. This one is within your reach, and it's the rotation map. Look at this. This slide is called rotation in R2. R2 is geometrically, we think of R2 as a plane. So this map formally presented as a geometrical description. So this map is formally presented as a geometrical description. You call it T sub alpha, or the letter may be different. Some people use R sub alpha. And that's the map which does this. The image of this map, T alpha of x, is the rotation of the original vector x around the origin by the angle alpha counterclockwise. That's how you formally present this map. My suspicion is that will be example of a linear map. Okay, so the presentation itself, unlike many examples in the yellow book, where you will see it's almost, I mean, your intuition will quickly suggest you that whether it's a linear map or not. With the rotation, it's not. I mean, it's a little bit harder to guess first, but suspicion is, and we will confirm it, it is a linear map, even though it's defined in such an orthodox way. You can see it on the or you can suspect it from the diagram. I made this diagram, and so the relations which we need to test for T alpha to be a linear map, they geometrically you can express them like this. It should be identical to rotative vector. For instance, if you test, say, second requirement B, the one which says a T of lambda x is the same as lambda times T of x. This requirement, if you now say it geometrically, it will sound like this. If this is my x vector, it should be identical to scale this vector by a scalar and then rotate it, or rotate it first and then scale it. The results should be identical, and for the rotation map, it feels like it is the same. For the A requirement, it should be the same if you have, if this is my y vector, this blue one, it should be the same if you add two vectors, and that's the red one, and then rotate it. Oh, well, yes. Oh, went too far out. Or you rotate them individually first, that's a T of x rotation, it's T y rotation, and then you add them. So when you look at this geometrical diagram, it gives you the reassurance that it looks like linear map, the rotation map is linear. Now look how we're going to confirm this. We don't have much. Okay, we have 2 minutes left. I will outline the scheme, and then I'll make the rest of the uploads. So what I will do instead, rather than testing that the rotation is indeed the rotation indeed satisfies the requirement A and requirement B, as we suspect from this diagram, I will do different thing. I'll make a suggestion for the map. I claim that the rotation map will have this matrix type structure. Okay, so if I introduce such a matrix A, you see, which is 2 times 2 matrix, filled with cos and sines in the proper order, in the proper positions. This map is linear map. We know it from the slide before. If you multiply by a matrix, it's a matrix type linear maps. We know these are linear maps. So what I will do I encourage you to do on this in the remainder of this slide is to see that this artificial, the map which I introduced out of the blue is indeed rotation. So rather than taking rotation and showing it is a linear map, we do the other way. We suggest a map, or we suggest a potential formula for rotation, and we test that this is a correct suggestion. So for that test, yeah, well, we don't have time. I'll think about that maybe next time we'll finish this. I'll think about that. But once again, if we want, here's the steps. I repeat this once again for you. What you need to do, you need to see that the map like that is indeed a rotation. Maybe it's too. Oh, next time we'll see what happens. Any questions? I don't want to take any of your time. If you don't have any questions, thank you very much. We're done today. Thank you.